Hello and welcome to today's webinar. I'm glad you've taken the chance to join us today, and I hope you find some useful information out of the content that we have for you today. My name is David Cash. I'm a member of the marketing team here at Mountz, and again, I'm glad that you've joined us to take a look at our topic today, which is a guide to the fundamentals of torque control. And this is going to be a little bit of a beginner's look at torque. So hopefully, if you have some experience with this, you're going to learn some of these things that you may not have known before. But we're going to look at, what is torque, why we use torque. We'll take a look at some torque terminology, how torque is measured, and then we'll look at the different types of torque tools that we have. And so let's go ahead and jump right in to today's presentation, and we'll take a look at what is torque. Now, the classic definition of torque is a measuring of a turning or twisting force. And it can get a little bit more complicated than that, but this is primarily what we are doing when we talk about torque. We're actually measuring the amount of force it takes to turn something in its perpendicular axis. And so when we do use torque, the thing that we're trying to achieve with torque is going to be the actual what we call clamp force. And so the definition of clamp force is a measurement of the generated tension that is indirectly controlled by an applied torque. And so what does this mean? And let's go ahead and take a look at this graphic. And this is probably going to help us show what the clamp force actually is. And so as we turn a nut, we're applying our torque or our twisting force to that. As we do that, the bolt tension there is being elongated, and that's causing the force from both parts to push together. So we have force from the top and we have force that's happening from the bottom, and all of that is generated by the tension that is created in the bolt from the amount of torque or turn that we put on that fastener. And so if we think about the bolt itself as a spring, and as we stretch that spring, it is providing more tension to that. And so the things that we need to look at here is going to be the torque that we use is giving us tension, which provides us with the clamp force. And that's why we use torque to do that. There are other ways to create tension in a fastener, but they really don't work that well in an application or an assembly type of process. And so that's why we use torque to do that. And if we look at a particular fastener itself, now when we talk about the fastener being able to stretch, and that stretch there is the tensile strength of a particular fastener. And each one has its own unique properties on how much that fastener can stretch before it actually goes to the yield point or actually breaks. And this is another thing that we need to consider when we are using torque for that. And so if we take a look at this animation here, what you can see is as this rod here begins to stretch, you can see the actual rod here begins to deform. And at that point, that's when the fastener has reached past its actual yield point. Now, if we bring this, the fastener has the ability to come to a stretch state, and then when it's relaxed, it goes back to its original shape. That means it's within its elastic region. But once that fastener gets to a point where it actually deforms, it is in its plastic state, and it will eventually go ahead and break. And this is what it would look like if we were to put it into a graph form. Our very first peak there is going to be our yield point. And everything below that, the fastener will return to its original shape without any deformation. But once we go past that yield point, that fastener will remain permanently deformed, and it is in the area of where it can actually break. Even though the fastener itself is still intact, any type of shock, vibration, or drawing will cause that fastener to break. And so one of the things that you will see when we talk about the specifications around a specific fastener, a value that is often given is the proof load. And the proof load of that fastener is typically going to be about 85 to 95% of the yield point. And so we want to make sure that we are within that window or below for us to be able to use that fastener correctly. And so this would be an example of a fastener that was stretched past its yield point, and a fastener that is not. Obviously, the elongation and the threads that have been narrowed at the point of the fastener there, that is showing us the actual deformation, and that fastener is then in the plastic region and is susceptible to breakage. So when we are looking at actual torque, how do we measure torque? Now, we take a look at this animation. You can see we have our wrench here. It has a lever arm to it. And as that lever arm is being pulled, we are applying torque to our fastener. And so at 1 foot of distance with 2 pounds of force, we are adding 2 foot-pounds of torque. Now, if we extend the length of our wrench to 2 feet and we pull with that same 2 pounds of force, we are now applying 4 foot-pounds of torque. Now, so the formula for this is our lever length times our force gives us our torque value. So that's how we actually measure torque, but we also use torque analyzers to do this as well. And what a torque analyzer does is it actually takes the analog signal from the tool and it converts it to a digital signal, and that gives us our torque output that we can see with that. And so as we use a torque analyzer, we have a sensor that is either built into the analyzer or is a standalone sensor that's connected to a handheld unit. But this way that the sensor works is through the use of a strain gauge. And the strain gauge is kind of it's a postage size little sensor, maybe a little bit less than that, but it is an electrified circuit. And if there is any bend or if there is any tension put onto that strain gauge, we can measure the difference in the amount of resistance that happens within that sensor. And that allows us then to convert the torsional forces on the sensor to a digital signal. So if we look at this in a kind of a real life application, we have our strain gauge that is laminated onto a piece of stock. And as that stock gets turned or allows torsion and there's that flex, that strain gauge, as we measure the resistance that happens within that, that is going to give us our value that we can correlate to the actual torque value. And so this is done through the use again of the way that the sensor is calibrated. And so this is, again, just an example of how the sensor itself will flex with the stock for the use within a static type sensor. But we get this, the values that are from the resistance that happens through the actual calibration process of the torque analyzer. And we use that same torque formula of length times force. And in this image, we have weights at a certain poundage that is connected to a segment arm that is connected to the actual sensor. And so as weight is applied at a certain distance, the resistance value of that sensor is giving us a value, and then that value is then correlated to the particular amount of weight that is on the analyzer. And so this is done in several points throughout the range of the actual sensor. And that's how we use the static reaction type sensor to measure the torque that is being generated. And so if we look at the actual traceability of how this then would work, if we were to calibrate a torque screwdriver on a torque analyzer, that screwdriver is traceable to that analyzer. The analyzer then is traceable to the calibration of the segment arm and the weights that are being used for the calibration of the torque analyzer. And so the screwdriver is traceable to the analyzer is traceable to the weights and segment arms, and the segment arms are then calibrated to the actual weight that those are providing in distance. And so all of that is the traceability map for a specific tool. And so that's how that scenario works. And so that's going to lead us to our poll question for today. And it's a pretty easy yes or no question, but do you have a torque analyzer in your facility that is being used for testing torque? So let's go ahead and run that. And give me a second here to grab a drink of water. All right, so it was very close in the results. We were almost at 50%, slightly under 60%. So 59 to 41 in the yes categories for the torque analyzer. So thank you very much for participating in the poll. And let's go ahead and continue on with the rest of the presentation here. One of the other things that we talk about when we're dealing with torque is going to be the unit of measurement that are being used. And in North America, in the US, we typically will see a lot of imperial units, which are foot pounds, inch pounds, and inch ounces. And this is very similar to the unit of scale that we use for other things within the measurement of feet, inches, and ounces. But to break it down, there are 16 inch ounces in 1 inch pound. And then there are 12 inch pounds in 1 foot pound. And so that's how we measure those particular units. Very similar to what we talked about when we actually are using a torque wrench. If we're at 1 foot pound of length with 2 foot pound or 2 pounds of force, that's 2 foot pounds of torque. And so that is the imperial unit. Then we have the international standard, which is going to be in Newton meters, or it could be Newton centimeters or Newton millimeters. But this uses a different value for its units, and this is derived from Isaac Newton. And if we have our lever arm or our moment arm at 1 meter, at a Newton value at the end of that, that is going to give us 1 Newton meter. And so 1 Newton is equal to about 0.2248 pounds. And the Newton value itself is the force needed to accelerate 1 kilogram of mass at the rate of 1 meter per second squared. And so this is what we are looking at when we're talking about Newton meters or Newton centimeters. One other thing about Newton meters is that it is an international scale. It's not a metric scale, although it does use meters and centimeters within it. It's only half metric. So that is one thing to keep in mind. But the metric standard uses kilogram force meters, or gram force centimeters, or kilogram force centimeters, or kilogram force meters. So it is the same concept of a kilogram or a gram at a certain distance in centimeters, meters, or millimeters in that. So that's the difference between the metric standard, the international standard, and the imperial standard when we're looking at unit of measurement. And so if you ever want to go ahead and you need to convert a specific value, on our website, we do have a conversion calculator. You simply pop in the value that you have, hit convert, and that will show you in all the units of measurement what that value would be in that particular unit of measurement. And so that makes it kind of easy to be able to do that. Now, when we're looking at torque tools and the different styles of tool, if we look at a torque screwdriver, the screwdriver itself is, you simply turn that screwdriver, it's going to reach a certain amount of force, and then that screwdriver will simply slip, and that will be the amount of torque that was generated on that particular fastener. And this is primarily how all torque screwdrivers work. And the difference between what you may see with different torque screwdrivers is going to be how they deal with a clutch mechanism in the actual torque delivery. And so in most cases, we are dealing with the ability to actually compress a spring in the torque delivery, and how that spring gets compressed is going to be the difference between different types of or different brands of screwdrivers. And so if we take a look at the system that we use, we have a radial cam that has 6 different lobes within that cam. As the screwdriver is rotated, those 3 ball bearings will ride inside that cam and then push on another ball bearing, which compresses the spring. So we have that radial cam design that we use with the different ball bearings systems to be able to give us a really nice, smooth, and consistent compression of that spring. Other types of screwdrivers will use a ball clutch system, where that ball or a ball bearing will ride up over something and then reset. And so that is where you're going to see the difference within one screwdriver to another screwdriver is how the spring compression is handled. So one thing to keep in mind there. The next type of torque tool that we are going to be talking about are going to be torque wrenches. And there are a number of different styles of torque wrenches, and they primarily all work on the same function that we talked about with the screwdrivers. We're compressing a spring to a certain value, and that is giving us our torque value. And so with the different drivers that we have here, starting on the left is going to be a cam over style of wrench. And this acts just like a screwdriver would as well. So as we pull on that wrench, it's going to cam or slip once it reaches a certain value, just like the screwdriver. And that will allow us not to add any additional torque to that actual assembly. As we pull it, it's going to completely slip and then it can just keep going around and around, but it is not going to give us the ability to add over torque to that fastener. The next style of wrench there is going to be a breakover style wrench. Now this wrench will allow us, as we use it, it will simply start to break at the pivot point. And once that has done that, that is the amount of torque that has been delivered at that particular value for that wrench. So the breakover wrench also gives us that ability not to over torque, gives us a really big signal that torque has been achieved. The next style of wrench is going to be the most popular and most widely used wrench in the world, and that is going to be a click wrench. Now, for most click wrenches, the spring compression happens with inside of the tool itself. And then there's a little block that is inside of there. And once there is a certain amount of pressure on the spring, that block will simply rock to the side. And that's where we get the click. So that's called a jump block or pivot block on there. And once that happens, the operator needs to release the wrench to not add additional over torque. And so the click wrench itself is a signaling type of tool. If the operator pulls past the signal, they are adding additional torque to the actual application. If they double click or triple click, and in some cases, we're adding almost double the amount of torque that the operator is trying to achieve by doing that. So the operator is very, very dependent, or excuse me, the tool itself is very dependent on the operator. And so it just depends on who's using that, how much torque is being delivered to the application with the use of a click wrench. Again, it's a widely popular wrench, very inexpensive, but it's highly influenced by the operator. So if you do see areas where you're having over torque issues of fasteners that may be failing, and there's a click wrench involved, the operator is usually the issue there. Now, the next wrench within the torque wrench family there is going to be a digital style wrench. And these typically will use some type of sensor to be able to tell you once you've hit a certain value. But just like the click wrench, there is nothing to prevent the operator or the user to go past the actual value that's being used, unlike the cam over or breakover style wrench. There are also dial torque wrenches in there as well. Again, those are signal wrenches, or are going to be able to provide you with what those values are of the wrench that are being used. So that, again, for most of these, barring the electronic wrench, they're all dealing with that same type of compressing a spring to a certain value, and then that is providing us with the torque that we are looking at. The next item or the next tools that we'll be talking about are going to be electric torque screwdrivers. Now, these come in many different styles of tools. You can have tools that have a soft stop feature, tools that have a soft start feature, tools that have adjustable RPMs, tools that have an automatic reverse feature. There are a number of different styles of electronic torque wrenches for specific types of applications. But these, again, use the same type of torque control. There is a clutch mechanism within the tool itself, and that clutch is controlled by a torque spring. And so if we take a look at this example of a torque screwdriver, if we remove the cone of the tool there, you can see this is where that spring lives. And as we adjust the amount of pressure that is on the spring itself, that is going to be what is generating our torque value. And so with the reference marks that are located on the tool, those again are just reference marks. They're not providing us with what the torque output is for that screwdriver, but we can correlate those reference marks if we use a torque analyzer to validate where that is for that specific tool. And then we can use that type of reference. But again, the spring is what is being compressed to give us the actual torque output. And that's how most electric torque screwdrivers function. The next type of torque tool are going to be the DC torque control tools. And then these are processor controlled tools that give us a great deal of freedom in how we look at specific applications. They give us complete control over what happens from the moment that the trigger is pulled until it finally stops with the operation. And so these particular tools give us the ability to save data collection files. We can do graph rundowns of a specific torque. They give us the ability to have multiple different presets that we can use within a specific range of a particular tool. And they come in different types of configurations, from right angle tools to inline tools, and also pistol grip style tools. But the real big advantage to the DC tool is control. There are tools that are built with sensors within them, so we can capture the actual torque reading that happens during the rundown. That information can be saved, can be integrated into an MES system. And again, it just gives us a lot of control, a lot of data that we can use to help us be better within the process. And also, again, collect information that we might need within the process of a particular assembly. And then the another type of tool with that is going to be a pneumatic style of tool. Again, these particular tools compress a spring, but the big advantage of using a pneumatic tool is that we can go much higher in torque values than you can with an electric tool. There are electric torque screwdrivers that can go up to 80 inch-pounds or so, but most of them live probably under 25 or so inch-pounds and below. But with the pneumatic tool, you can go much higher in there. And if you need to go extremely, well, maybe not extremely higher, but and you want to be able to control the reaction that happens with a tool that shuts off at a higher torque value, then you can move into a pneumatic pulse tool, which uses a unique clutch mechanism that has a hydraulic cylinder or a hydraulic mechanism that allows us to capture the torque at a high value without giving any or little reaction to the operator during the use of that particular tool. The downside is that they are not as accurate as you would see with a standard pneumatic tool or an electric torque screwdriver or even a DC tool as well. But the pneumatic tool does the same thing that we talked about before, is we're compressing a spring to provide us with a torque value for that particular tool. And then finally, we have what would be considered really high torque values from, say, 1,000 foot-pounds up to 35,000, 50,000 foot-pounds. And that would be the use of a torque multiplier. And that can be, again, used with a pneumatic style of motor, a pneumatic stall motor, or you can be used with an electric motor, like you see here in these pictures, or it can be just using a standard wrench with an input, and then we're relying on the gear package that is within the tool to help us provide the output that we're giving. And so that could be anywhere from 4-to-1, 8-to-1, 16-32, depending on the amount of torque that you might be needed to deliver with a particular input value. And we're going to give us that particular reading. And so the foot that you see on these tools that come off the spline there, that is where the actual torque gets generated. So we're actually setting that foot against, typically it's the next fastener over. And so that is providing leverage for the actual multiplication that is happening within that. And so if we take a look at an example of a hand multiplier that's in use, this could be like an 8-to-1 type of multiplier. So if we put 200 foot-pounds on the input and we're at 8-to-1, then we're getting 1,600 foot-pounds as the output. And so as that wrench is being used, it will click at 200 and then we can get that output. And again, it's all dependent on the gear package that is being used. But for higher torque values, you can use this style of tool. So with that, so there was, kind of a lot of what was going on there, but the big thing or the big takeaway that we would like to give you is that understanding that the amount of torque that's being applied to a fastener is helping us create tension, which is providing us with a clamp force that is needed to keep our parts together, to keep them from having any movement. And that is the whole reason that we use torque within the manufacturing process. And so the torque gives us the tension, and then the tension gives us the clamp force. So I hope you found some useful information within today's session. So let's go ahead and see if we have any questions or answers. So Chris, do we have any questions?
Morning, Dave. Yeah, the first question we had is, with like a hand wrench, does the hand position on the tool influence the torque output?
So it can most certainly. When we're looking at a click style of wrench, where we hold our hand on that is going to determine how much torque is being used. And that's because the fulcrum point is inside the end of the tool, or excuse me, inside the tool itself. And so as we move our hand closer, we're going to be changing that distance formula that we talked about with the distance times force. However, if we use a cam over style wrench where the fulcrum point is going to be at the end of the tool, it doesn't really matter because we're generating that same torque times force. That ratio is always going to be the same. So with a click wrench or even a breakover style wrench, the hand location is going to be critical to make sure that you're getting the right torque value.
All right, Dave. Next question we had was, what's the difference between a tool's accuracy and repeatability?
So if we look at a bullseye target, and we have a tool that is repeating within a certain area very well. So all of the results for the readings are in a nice tight pattern. That would be repeatability. How close those are to the actual target is going to be the accuracy. And so we may have a tool that's very repeatable, but it's not very accurate. And so we may need to adjust the tool to move closer to the target. And that would be the accuracy. Now we may have a tool that is accurate on average, but the points are a little bit scattered. But if we average those out, we get good accuracy. And so that would be a scenario where the tool is accurate, but not very repeatable. And so obviously the ideal scenario would be that we have an accurate tool with good repeatability. So I hope that makes sense.
All right, Dave. The next question we had was, can you explain a little bit more about like joint relaxation, how it affects the torque process?
So when we are dealing with trying to secure the clamp force, in some scenarios, you may be dealing with a really soft gasket type material. And as that gets compressed, it then will go ahead and relax. And so that can cause some initial torque for that to not be as secure as we might like. And so when we're dealing with those types of joints, we may need to exercise that joint a little bit and then go ahead and seat it. Or we may need to do a torque plus a little bit of angle to turn it. But there are those types of scenarios when we're dealing with really soft gasket type of joints where we may need to take a look at how the torque may be, or how the relaxation of that joint may be affecting the torque values, and then make adjustments to that.
All right. Next question we had, Dave, is when you're using a torque analyzer in like a verification process, is there a certain mode that you should use for that process, or does it depend on the tool type?
So it's going to depend on the actual tool that you're using, on the mode that you would want to use with the torque analyzer. In most cases, you'd want to use the peak mode. There are typically 3 different modes that are mostly used. A peak, which is going to measure the highest torque delivered. We have a track mode, which will very much like a scale give us the value that's being applied to the load at that moment. And then we also have a first peak mode, which is going to show us the very first peak that it sees, and then it disregards any additional torque after that. And so for peak mode, we would want to use that with either pneumatic clutch tools, electric clutch tools. You can use those with DC tools, with standard hand screwdrivers, or cam over style wrenches. And then you'd want to use first peak mode for calibrating click wrenches, because we are really concerned with the click wrench on where that wrench clicks, because that is going to be the indication of what the torque value is. And then for the track mode, you would use that for dial type screwdrivers and wrenches.
All right, Dave. Next question we had was, can you describe the difference between static and dynamic torque?
So a static torque is going to be where the wrench actually, or if you wanted to use it in the scenario of a particular moment at when torque is achieved. And then dynamic is going to be the measurement of a power tool as it's being used. So you have a moment would be static, and then a continuous would be dynamic.
All right, Dave. Next question we had was, is there like a chart or some type of way to get guidance on torque value to be assigned to a certain fastener, or do you need to do some type of destructive testing to determine a spec?
So fastener manufacturers will provide recommended nut factors or K-nut factors for a specific type of fastener. And then they may give a generic torque value to that. But typically you're going to want to do any type or do a destructive type of test to see actually at what point that fastener fails. Again, we want to make sure that we're within the proof load area of that fastener or below. And you want to do some testing when you're developing a torque spec for a particular product or part. So that typically will always be a better scenario to do than relying on a guide for a torque value. So doing a destructive test is usually the best practice.
All right, Dave, thanks. Next question is, does RPM, like the speed, affect the torque applied? And if yes, how do you determine an appropriate RPM value to use on a fastening application?
So yeah, RPM is going to affect the accuracy and repeatability that may happen within the use of a power tool. So typically the slower you can go, the better. But there are, scenarios where the production demands may cause for a higher RPM type of rundown, and not all joints are going to be as crucial as you may need to be accurate. So there are different scenarios in which you can use perhaps a DC type of tool where you can program the rundown to be at full RPM for most of the fastener and then slow the tool down to the seating and final torque. That is one way to handle that, but RPM definitely plays a part in the amount of torque that's being delivered within the use of a power tool.
All right, Dave, thanks. Another question we had was, when you're dealing with like a plastic part and the screw that's being used on it, is there a way to analyze the torque, its impact on that plastic part?
Yeah,
And
again,
any,
you
I guess,
can
cautions
use
to use?
Yeah, you can use sensors or torque rotary types of sensors to monitor the amount of force that's happening during that, especially if it's cutting threads, where you may be able to determine based on the amount of angle or turn that's being applied with that. But yeah, if you're looking at self-tapping type of applications, what the amount of actual torque may be happening to a destructive point, and then back that torque value off of that to make sure that you're getting a good fastening. That would be, again, the use of an inline sensor that was going to allow us to be able to see what the value is when that fastener fails. And in those scenarios, it's going to be maybe the plastic, obviously, that's going to fail before you would break a fastener, but that is simply going to strip out the plastic. So but that is typically how we want to do that, is monitor the amount of turn that's happening and at what point that particular part is going to fail, and then make adjustments to the output at that point.
All right, Dave, thanks. The next question we had was, is there any like preliminary visual inspection that can be done prior to a torque calibration process for a tool or different types of tools that can visually indicate it needs calibration?
Only if you're going to put that tool on a torque analyzer to do a routine check of that before that tool goes out for calibration. Typically, you're not going to be able to see unless that tool is providing too much torque, or if an operator has adjusted it and now you're seeing problems with lifted fasteners or stripped fasteners. But primarily, if you have the ability to do testing of that tool between calibration intervals, then you can certainly monitor the performance of that tool and then make adjustments either to the tool or have it sent out with it being outside the spec.
All right, Dave. I think we covered majority of the questions. Any of them that we weren't able to get to, we'll follow up after the webinar as well. So thanks.
All right. Again, thank you very much for joining us today. And if you have any questions, feel free to reach out and we will help you any way we can. All right. Thanks very much. Have a great day.